from National Taiwan University. So it's my pleasure to be here to give a short talk in this workshop. So my title of the talk is about algorithms and the software for text classification. Well, this is a very general title. And it seems that I have lots of materials. You see the outline here. But I have the privilege of doing like a continuous talk because yesterday I gave a presentation in a university colloquium. In that talk, I actually covered the second part, but not the third one. So instead, today, I'm not going to, I will focus on the third part in my slides. Therefore, the plan of my presentation will be for the first part to give you an introduction about our open source project, and then move to the third part. That's about some issues we faced in developing our software. So now for recently, we are doing some open source project for text classification. I think most of you here are familiar with text classification. So here are some examples. Each row is a data instance. So we have labels and then a sequence of words. And the problem may be, say, binary or multi-class. That means each document is associated with exactly one label. But it can also be multi-label, which is more complicated because each document may be associated with multiple or even 0 labels. But this is actually an area we'll study. However, we find out that tools to easily and conveniently solve users' problems actually are still somewhat lacking. For example, so if you check the multi-label classification, you can find out maybe more than 10 possible evaluation criteria. So you can consider things such as accuracy-based criteria, such as micro and macro F1, or you can consider ranking-based criteria, such as precision or MBZUAI. So which one should be used? And also, for data, they may have different situations. Sometimes you don't have many labels, such as you have only like 100 labels, but for certain applications, you may have millions or billions of labels. The way to handle such problems should be different. So then the question is, can we guide users to solve their problems? This is indeed difficult. We find out that so far for multi-label classification, we don't have some kind of like definitive recipes to tell users, say, okay, under this situation, you should use this kind of approach. And under that situation, you should use some other approaches. And this is a little bit beyond what the current automated machine learning can do. I think for automated machine learning, usually we need some, like for example, in the first talk this morning, we need a black box function. But now it seems I don't really have such things. So that's the difficulty. But anyway, because of the need for doing some applications, so a project called multi-label is an ongoing development by my group. Well, it's a simple tool with the following functionality. So we do end-to-end services from raw text until evaluation and analysis. And of course, we support common network architectures as well as conventional ones like linear classifiers. And we support easy hyperparameter selection. Then, well, of course, we try to cover both standard binary multi-class classification as well as multi-label classification. Yeah, but anyway, I have said that well, now we have a tool, but we don't have an automatic procedure to tell people how to effectively solve their problems. Yeah, so if you have better ideas, please let me know. I'm here to ask for your help. But now let me now I want to go to talk about a specific topic that we need to solve in designing this software package. That's an issue about whether we want to do a retraining process after hyperparameter search. So what is this issue? So here I have a figure showing a typical machine learning cycle. So in order to select hyperparameters, usually we split data to training and validation. Then, using the training data, we do the model training, we get the model. Then using the validation data, we get the validation results. That's the way how we choose hyperparameters. But then the question is, then after this is done, then we identify the best hyperparameter configuration, right? So sometimes we directly use the model with the best hyperparameters for use. Yeah, that's typically what many people do. But another thing is, should we take the best hyperparameters, then also include the validation data together to get a bigger set to retrain to get a so-called the final model? Yeah, so that's the question. Because in developing that software, we find out that should we do this or should we automatically do this for users or not? So now I have this issue called to retrain or not to retrain. So in many deep learning practice, people don't include the validation data to generate the final model. But if you look at some other machine learning methods in the past, such as support vector machines or logistic integration, well, in general, people do that. So they do cross validation to select the best hyperparameters. After that, then they use the best hyperparameters then to train the whole training set to get the final model. That's the way how people do things for SVM or logistic integration. Then an apparent reason of doing that is because more information is used. Now you include the validation set. But then we ask a question, why for deep learning, people may not do such a step, and why? But in fact, in deep learning community, people have realized such an issue, and there are already some studies. Actually, some people may think that this is an old and already solved issue. If you go to check some online forums, you find out that many engineers, they still ask about whether they should do this retraining step. So we tried to do some studies, but we found out that things are actually more complicated than we thought. So now let's check the difference between, say, deep learning and some traditional models. So we know that empirical risk only approximate the true risk. Therefore, in general, you don't need to accurately do the empirical risk evaluation. However, for support vector machines or logistic integration, people do that. The reason is that those are convex optimization problems. They are easier to solve. Yeah. So people check, like, say, gradient norm for stopping. So the reason is that, well, convex is easier, so training is not too time-consuming. And also, using gradient for stopping is quite convenient. So that's the situation in the past. But for deep learning, well, now you have convex optimization, and also for each training, it's so time-consuming. Therefore, early stopping is needed, and that's everybody is using right now. But how to do early stopping? usually this is by checking the validation performance. Right? So you have a validation set. So then you stop run. Then you run iterations until one time point. Then you find out that validation performance no longer improves. You stop. That's the way we are doing right now. And that becomes a question, a problem. If you want to do this retraining, it's not only for the retraining, all the available data are used, but our optimization process rely on validation data to do termination. Well, then the procedure no longer works. So that's the problem. But then, of course, we can develop some possible stopping conditions, such a situation. Basically, we want to use properties of training the best model in hyperparameter search. We use such properties for our stopping conditions. So here I use an example for illustration. Suppose in hyperparameter search for the best one, my training procedure is like this. Well, I set the maximum, the iteration bound to be 50. And I happen to use, say, 18 iterations. And at that time, my training loss is such a value, and my model parameter is called f star. Then I have some possible criteria. The first one, that's a very simple one. Let's just say, okay, now I include the validation set training, but I don't know how to do stopping. Therefore, I use a fixed number of iterations. So for example, now I just say, okay, I decided to run 50 iterations. And then for initialization, we'll start from stretch. And I call this fixed epochs. So this is a very simple possibility. Then the second one is to say, well, while training the best model in the search procedure, I used 18 iterations. So why not also training the same number of iterations? Therefore, for this approach, I call it optimal epochs. Then I just put all data together and I train 18 iterations. Well, this idea is also simple and it seems to be reasonable. Then there's another idea. I call this a function-based idea. So the idea is that I have this training loss. That means I have fit the training data up to a certain point. But at that time, the validation error is actually high. I have a bigger validation error. Now I include validations data for training together, right? So suppose the validation error should increase. So I just try to train until the loss of the validation set matches the training loss early. So here I mentioned this is in doing the combined training, if the loss value on the validation set matches this 0.040 for me, then I stop. But for this one, I can do some kind of warm start instead of initialization from spreadsheet. So there's several possible ways. And here are some sample results. And here I try 3 network models. They are typical for text classification. I have CNN, I have RNN, as well as BERT. The blue one is actually using the fixed number of iterations. The green one is using the optimal number of iterations. And the red one is this function-based. Well, we still need to check the result. So of course, the horizontal line is 0. So if I have values above 0, that means this retraining is useful. Actually, for the blue one, sometimes it is it is worse actually. But if you look at green and the red one, in general, they are above 0, and sometimes the improvement is significant. This is for CNN, as well as for RNN, as well as for BERT. So a quick summary about the result. So retraining seems to be beneficial for most problems, but the best strategy is now between the green and red one. Actually, here red is better, but in this place, actually green is better. So it seems that the best strategy is model dependent. That's roughly the observation. Well, I have run out of time, so let me quickly go to the next slide about some discussion. Well, I have a couple of questions here. So for me, as a package developer, should we by default do retraining after hyperparameter search? Well, if that's the case, then which setting should we provide? And right now, I have only studied text classification. How about the other applications, say like computer vision? Their network architectures are different, where we have similar observations. I don't know yet. And then right now, we mainly have empirical evaluation. So can we have some good theory for this issue? Okay, so thank you very much.
You actually have time for questions because you are the person who actually ended on time. So we can take 3 minutes of questions if anyone has questions.
I like to be on time. Yes.
Can you go back to the results slide there?
Oh, yes.
Three strategies.
Yeah. I didn't spend enough time to.
I think this was eventually clear to me, but the assessment that you're doing here for these is on some additional test set. Is that right?
Oh, yeah, right. There is an independent test set. So actually, it's very difficult to do this experiment. For every setting, I need to do complete hyperparameter search. Okay. Then after that, I do the retraining. Then I do the prediction on an independent test set. Yeah, it's very difficult to do this experiment. Yes.
And also as for the function-based one, you said you were inserted into like the optimal weights, like, or parameters on the whatever hyperparameter is optimal. Right? Do you is usually the loss val less or greater than the optimal one when you initialize it on the validation set, and then it goes down and you stop it at the previous clusters?
I actually have a table here. Okay, this shows everything. This is a good example. So for the first row, this no retrain means the information after hyperparameter search. So you can see that the training loss is this, but validation loss is actually high. It is high. But this is a case that so we intend to reduce this validation loss to match the training loss here. And we really get that. But the problem for this example is that then somehow we overfit the training part, the training subset. So for this case, actually, the function-based approach doesn't work as well as the Optima Apex one. So the Optima Apex one, for this example, you can see the training loss as well as the validation loss. They both match the original training loss. Therefore, no overfitting happens. That's a good case for this approach. Yeah.
Also, did we see the? I'm wondering if we, I'm not familiar with the metric you used on the final results plot, but I'm just wondering if the validation set is used in a number of just standard deep learning applications. Do you expect that the metrics that we compute can go up significantly? Like, is this a big increase when you use your strategies there?
Oh yeah.
Like the metrics here, is that significant?
Yeah. So at least for this data set, you can see 10% improvement. That's very significant. Oh yeah. You see this figure here? No, this is not. So this is actually 10%, more than 10%. So this one is significant. But for other, but another thing I didn't mention is things related to the ratio of data you use for validation. Okay, if your validation set is very small, well, then no need to do this. But you need a bigger validation set, then of course you need to include it for the final training. Okay, so thank you again.